Hello students, welcome to Legacy IAS Academy. Today we are going to discuss about the Nobel Prize that has been awarded in the area of physics. Who are the scientists who have been awarded with this prestigious prize and what has been their significant contribution in the field of physics for which they have been awarded this particular prize. So in this particular video we are going to discuss all these aspects in very detail, and also we are going to discuss about the strange world of quantum physics where all these scientists have worked upon and significant contribution has been made by them. So first of all, why this particular issue is news? So as we have discussed in last video as well, that with the award of Nobel Prize in the area of medicine, the season of Nobel Prize has begun, and the second dimension or second subject where the Nobel Prize has been provided is in the area of physics. So on the 4th of October, the Nobel Committee have announced the name of three physicists as Nobel laureates for this particular year. So who are these three physicists? The first physicist is named as Alain Aspect, who is working in the University of Paris-Saclay and France. The second physicist is John F. Clauser of John F. Clauser and Associates, based in California of the United States of America. And third is Anton Zeilinger, who is a physicist working currently in the University of Vienna in the Austria. They have been awarded for the experiments which have been made by them in the area of entangled photons, and that also have established the violation of Bell inequalities and have pioneered quantum information science. Now, all these terms seem very technical and very scientific in nature. So, in the later part of this video, we'll try to address and explain in more lucid details that what these terms stands for. So, as per the press release published by Royal Swedish Academy of Sciences, which basically award Nobel Prizes every year, this is the press statement that has been released. So, let us try to understand what are the experiment where these scientists were involved. So, experiment relates to the field of quantum physics and more specifically the area of quantum entanglement. Now, what is quantum entanglement? We'll discuss in later part of this video. So, as far as the quantum entanglement is concerned, the scientists, especially John Clauser and Alain Aspect, have basically formed up this concept and have helped in developing more complex experiment, more error-free experiment, more bias-free experiment to demonstrate this particular phenomena of entanglement and prove that this phenomena actually happens. Second, as far as the Anton Zeilinger is concerned, he has made a very innovative use of this concept, a theoretical concept of quantum entanglement, and has made it use it in a practical application such as Bell pairs, and he also have innovatively used the quantum entanglement for the application such as quantum cryptography as well as the quantum transportation. The both of the phenomena, quantum cryptography as well as quantum transportation, can be used in the future quantum computers. Now, quantum entanglement is a very strange phenomena, something that our mind is not able to grasp properly because we live in a classical world, and that is why quantum entanglement has also been phrased by Albert Einstein, the well-known physicist, as spooky action at a distance. So what basically is the principles and the basics of quantum theory? So first of all, we know that somewhere in the early 18th and 19th century, many people and many scientists believe that they have known everything they need to know about our world, our universe in general. And the most significant contribution in this era has been made by the well-known physicist Sir Isaac Newton. And Sir Isaac Newton is considered as the founder of the very important and the main branch of physics called as mechanics. Now, mechanics, we have two parts. One is called as classical mechanics and other is statistical mechanics. So what basically is classical mechanics? In simple term, classical mechanics can be described as the physics or the science behind the movement of solid objects. Movement of solid object can be as small as a tennis ball and can be as large as our Earth or even Sun and the other bulkier or celestial, heavy celestial objects of our universe as well as solar system. So their movement and the science behind their movement is governed or can be explained by the phenomena of classical mechanics. For example, if we want to know that where exactly after throwing of a tennis ball, the ball is currently situated, we can use the phenomena of classical mechanics to know the trajectory, to know the direction and know the velocity of this particular ball. Similarly, if we want to know that what speed at which our particular car or bike is going at, we can use the phenomena of classical mechanics to arrive at that particular conclusion as well. However, several other scientists basically unraveled a new world which was hidden beyond this level of the world which we are continuously interacting with in our daily life. and to explain the behavior of subatomic particles such as light particles or light quanta, a new phase of physics or new branch of physics has emerged that is called as quantum physics. And thus the main objective of quantum physics, the main reason why quantum physics came into existence, was to simply break down the classical mechanics concept at the subatomic level. Because when the scientists who have made a stellar contribution in the field of quantum physics, such as Werner Heisenberg, Max Planck, Niels Bohr, as well as we can say Schrodinger, all these scientists try to explain that whatever concepts or whatever science or whatever explanation we can give to explain the classical world, the same explanation, same science, same concept cannot be used to explain the world which exists at the subatomic level. That means when we break the atoms into much more smaller form, there we have a different kind of physics that is operating. And what kind of physics that is operating there? To explain that, we have the quantum theory. So let us try to understand what is the difference between the classical world and the quantum world. So again, to elucidate my point, suppose that if a tennis player has thrown a ball or has a hit ball, the ball will follow a particular trajectory and will go and reach at particular destination. So what will be the trajectory of this ball? What exactly will the velocity of this ball? At what speed the ball will accelerate and further decelerate? All these things can be basically understood and basically calculated with the use of classical mechanics as given by the Newton, obviously by using his three different laws, the first, second and third law of Newton's gravity. However, when we go into the quantum world, where we are dealing with the objects which are not solid objects such as tennis ball, but are very weird quantum objects such as light quanta or such as subatomic particles are there, elementary particles such as bosons are there, all these particles. So they do not follow this classical principle. And to explain this, we have the quantum mechanics. Now, the most important part or the characteristics of the quantum physics is something that is referred as quantum entanglement. So what basically is the quantum entanglement? And this is our main topic of discussion today because the Nobel laureates have done most of their work in the area of quantum entanglement. So in simple terms, quantum entanglement can be defined as when a pair of particles, for example, we can take photons, which is light particles. So when the pair of particles such as photons are allowed to exist in a shared state and they have complementary properties irrespective of their distance, then they are said to be in a state of quantum entanglement. Now let's make it more simple. For example, we have photon A and we have photon B. So they basically, what it means that they have a shared state. Shared state means they have complementary property. For example, in simple terms, we talk about the velocity of particle A. Velocity of particle A will determine velocity of particle B. Similarly, if suppose we have certain color of this particle, so the color of particle A will determine color of particle B. And it does not matter how far they are. They are basically entangled. They are having a shared state. That means if there is changes that is happening in the properties of particle A, that will obviously cause changes in the properties of particle B. Thus, though they are not basically exerting any kind of force on each other, but since they are in the state of quantum entanglement, the change in the properties of behavior of any one particle will automatically change the behavior and property of the other particle as well. So this is the whole essence of quantum entanglement. Obviously, it does make very little sense if we try to understand this in our classical world by giving a classical example. But anyway, let us try to break down and try to see that what can be the equivalent classical example of quantum entanglement in our which we can understand and do the experiment ourselves in the everyday life. So for example, suppose we have two boxes, box A and box B, and we have two different colors of ball. Suppose ball is of blue color, the other ball is of red color. So if someone put a blue cube or a red ball in separate boxes, you can tell which is just by looking into one of the boxes, since you know that we have either blue cube or we have either the red ball. Now if you open the box number A and suppose you find that there is a red ball inside, then you, without looking at the box B, you can automatically tell that obviously there need to be a blue cube in the other ball. This was the case even before you check the box. And even if you have not opened the box, you know that in one box we'll have the red ball, in other box we'll have the blue cube. However, in quantum physics, this is not so simple. For example, if we try to understand the same example at the level of quantum physics, an object can be a blue cube and a red ball at the same time. It is only upon observation that the object decides to be one or the other. That means if you have two boxes, box A and box B, if you are looking it from the quantum concepts, you cannot say that one box will have the blue cube and the other box will have the red ball. What you'll have to say in quantum physics, that in both of these boxes, two possibilities there. In box number A, either we can have blue cube or red ball, or not only that, we can say that in box number A, the ball have or the matter have both property. Is it a blue cube and it is also a red ball. At the same time, box number B also have two different property. Inside it, it is a blue cube and the red ball. So if two such quantum objects are entangled and put in separate boxes, it is only when you see that one box has a blue cube, then you know the other object has become a red ball. Now see, this is very, very important point. The main difference is that in the classical sense, it does not matter whether you observe or not observe, whether you open the box or do not open the box. The things does not change, the fact does not change that one box will have the red ball, the other box will have a blue cube. But this is not the case at quantum level. At quantum level, observation is very, very important part, because unless and until an observer is not observing the quantum state, the ball or the matter, the object inside the box will have two simultaneous state or two states at same time. It will be blue cube and the red ball, as well as in the other box also the matter or the object will have the nature of having blue cube as well as the red ball. So that is what makes quantum physics very confusing as well as interesting at the same time. Basically here what is operating is something that we can call as principle of superposition, where on the single object two different properties are superimposed unless observer tries to observe one of the boxes. This is something that Einstein was not very much happy about or was not able to explain properly, and that is why to counteract these argument, he published along with his colleagues a paper that is called as EPR paradox somewhere in year 1935. So the most significant contribution, because Einstein, other his we can say followers and these students were not happy with this quantum concept and not able to properly explain that how this whole quantum entanglement is happening. John Bell, a Scottish mathematician, came into picture, and he has made a stellar contribution in the area of quantum physics. So what he said, the first of all, his major contribution was he was able to show mathematically what was required to be done by experimentalists to establish the phenomena of entanglement. Because as of now, quantum entanglement is just a concept, is just a theoretical phenomena. We do not have any experiment to explain that whether it is really happening or not, or if it is happening, then how it is happening. This was something that was done by Bell, and thus he gave a theorem that is called as Bell's inequalities. And in simple term, you have to understand that if Bell inequality exists or if Bell's inequality is proven, that means quantum entanglement is not real. While if the Bell's inequality is unproven or if it is broken, that means Einstein was wrong and quantum entanglement indeed is real. So Bell, explaining this concept, says that the indeterminacy of the color of the ball is purely a quantum phenomena. But at the same time, he also said that how these properties of the ball is changing, that is determined by something that we still not know, and that what is termed as a hidden variable, that was also accepted by Einstein, that there is some hidden variable that is changing the properties of these quantum particles when we are observing one of the quantum particles. So what is the most strange point about quantum physics? First of all, as we discussed, it completely goes against our everyday experiences. That is the first point. Second, most of the quantum physics is based on not a pure calculation, not on the exact calculation, but it is based on the probabilistic calculations. And also there is an underlying principle which is called as uncertainty principle, which is first of all explained by Heisenberg. In simple terms, uncertainty principle says that you cannot determine two states or two properties of any object with equal accuracy. That means we take example of a biker that is going on the bike. So when the biker is moving on the bike, he is covering certain distances. The distance can be measured by suppose x, and at the same time he is also driving the bike with certain velocity that we can call as v. So when the biker is moving, he is covering certain distances and he is also moving with a certain velocity. So as per the Heisenberg's uncertainty principle, which is a very important concept of quantum physics, if someone is trying to measure the distance that biker is covering, or if someone is trying to measure the exact location at which the biker is right now, he will be able to not measure properly what is the velocity at which it is going. That means the more accurate the measurement of distance is, less accurate will be the velocity measurement, and vice versa. If someone is focusing more on measuring accurately at what velocity the biker is traveling, less accurate will be the distance to which he can be pinpointed. So this is something that is called as uncertainty principle that is used in the quantum physics. That means if suppose a quantum matter such as photon is there, you cannot exactly determine with equal accuracy what is its exact location and what is its exact velocity. So apart from that, we can also try to understand the strangeness of quantum physics with a thought principle that was given by Erwin Schrödinger. So Schrödinger has given an example of a cat, and he said like this: suppose that there is a box in the cat. Suppose there is a cat in the box, and if the cat is present in the box and this box is closed, at the same time we have suppose a radioactive substance that is present in the box, and after a certain time the hammer will strike automatically and will break this beaker or break this we can say glass or any object where the radioactive substances is. And when the glass beaker is broken, gradually radioactive substances will be released and the cat will, due to radiation poisoning, will die. But this is the problem here. Unless and until we do not open the box, we cannot say exactly with 100% accuracy whether the cat is alive or dead. So if we try to understand this from the quantum physics principle, unless and until an observer is not able to open the box, the cat has two states. Now see, this is very strange seems as per our classical understanding, but this is actually what is going on in quantum physics. The quantum physics says that unless and until one observer does not open the box, the cat will be existing in two states. It will be in the dead state as well as it will be in the state of aliveness. Only it is when the observer opens up the box, then only he will be able to see that whether the cat is alive or cat is dead. So that is what the quantum physics is all about. There is a degree of probability, there is degree of uncertainty, and only when the observer is involved, that degree of uncertainty changes. This is something that also been explained from the perspective of light. That means light, we know, behave both as a wave as well as particles. But when light will behave as wave and when will light behave as particle, this is something that is determined by what kind of observer is looking. For example, if we do certain experiment where we try to examine the wave characteristic of light, light will behave as a wave. Whereas if we do the other experiment where we try to examine or inspect the particle character of light, in that case light will start to behave as a particle. So whether it will be having as a wave or it will be having as a particle, that determines on what kind of observer is doing what kind of experiment. So in this regard, Einstein was very much unsatisfied with the all concept of quantum physics because he was not able to properly explain this. And there's something that also goes against the major theory that Einstein has propounded called as general theory of relativity as well as the special theory of relativity. So let us try to understand what is Einstein's general theory of relativity. So Einstein's general theory of relativity is basically nothing but has a basis on in the Newtonian physics, but it tries to explain the Newtonian physics in the terms of space-time continuum. What it means? It simply means that Einstein said that, for example, if you talk about the force of gravity, the force of gravity is not exerted or is not a kind of real force that is being exerted by one celestial body on the other celestial body, but the gravitational force is because as the celestial body is very heavier in nature, and when it is rotating or revolving in a space, so space is nothing but a kind of fabric. If you try to understand from the Einstein's imagination, the whole space, and not only space but also time, is a kind of a fabric like or rubber like we can say this rubber like structure is there. So if heavy object is placed here, suppose this is our sun, so suppose if you place a heavy object such as iron ball in the rubber, what will happen? It will create a depression around it because of its weight. The same thing happens in the space as well. When the sun is placed here, due to its heavy weight, due to its heavy mass, it is creating a distortion, it is creating a kind of depression in the space. And due to this depression, what happens? The other celestial objects such as earth and other planetary bodies, they try to move in this kind of area, they try to move under the influence of this kind of object, and this is what we call as the force of gravity. If try to understand this, the application of force of gravity, of this application of this Einstein's general theory of relativity, how we can understand this? Simple. If suppose we are looking from the earth and we are looking at two stars, this is star A and this is star B. Now if suppose there are no celestial object in between earth and these stars, in that case light emanating from the stars would have traveled in a straight line and would have reached here, and then we would have made a image of these two stars in a straight line. So in the normal circumstances, without the presence of any celestial object, without the presence of gravity, what would happen? We would have able to see a star in the clear line. But this things changes when there is a presence of some celestial object in between. For example, we know that between stars and our Earth, there is a heavy celestial object that is also a star, which is the sun of our solar system. So as we discussed, Now, due to the position of sun, due to the presence of sun, what will happen? The space-time around the sun will be distorted, will be kind of depressed, and thus when the light is moving from this star toward the earth, they will not be able to travel in straight line, because now the space is not straight, it is kind of depressed area. So the light will cover, or light will travel in a distorted path, light will travel in a kind of disturbed path, and that is why the actual movement of light will be something like this. It will seem that it is bending toward the sun, but we know that our image from our eye can only form in the straight line, and that is why the perceived position of star will be here and perceived position of star 1 will be here, while the actual position of star 1 is here and actual position of star 2 is here. So this is whole theory, or this is something, a concept that can be explained by Einstein's general theory of relativity, that the presence of every celestial body distorts the space-time structure around it, that also causes changes in the direction or the velocity of the flow of light or flow or velocity of any other celestial object. Apart from that, there is other relativity theory given by Einstein, that is called the special theory of relativity. A special theory of relativity basically tries to explain the direction or the travel direction as well as the speed of movement of any particular object. And in this regard, Einstein has clearly said that there can be no signal, there can be no such movement in our universe that can happen faster than the speed of light. That means every signal that is moving from one place to another place need to follow this principle. They cannot travel faster than the speed of light. Otherwise, we'll go in the past. Now, that is something topic, that how on basis of this we can understand the time travel and all these things, that we'll discuss in maybe some other video. So now, what is quantum teleportation? By using the principle of quantum physics, quantum teleportation refers to transferring of quantum information from a sender which is at one location to a receiver at a certain distance away. Now keep in mind, quantum in teleportation that we generally see in the movies or TV shows, where a person is able to transport himself from one place to place other place, that is not actually quantum teleportation. Quantum teleportation simply means the transfer of quantum informations only. It is not actually the transfer of physical object, but it is transfer of quantum information. However, this principle can later used for development of quantum computers, which can be hack free. For example, for transmission of one information which is in computer A, suppose information X is there and there is a computer B where this information has to be transferred. So by using the principle of quantum entanglement, quantum superposition and quantum teleportation, the information X from computer A can be sent to computer B without actually sending this information. Why so? Because X is entangled with Y, and thus if we changes the characteristic properties of X, the change in characteristic of properties Y will already be obtained. So that means we are able to send the information without actually sending information. And if we are not actually sending information from computer A to computer B, obviously no one can try to intrude and extract this information while it is in the process of transferring. So in this regard, we have understood till now what is the basic principles of quantum physics, what is quantum entanglement, what is quantum teleportation, and what has been the what has been the criticism of Albert Einstein against the quantum physics. So in this regard, let's try to understand what has been the contribution made by the current or present Nobel laureates. So first of all, if we talk about John F. Clauser, he basically was the first person to design experiment to test the quantum entanglement. The results were a clear violation of Bell's inequality. And we have discussed right now a slide before that if the principle of experiments are able to violate Bell's inequality, that means quantum entanglement is real and Einstein is wrong. On the other hand, due to this experiment, he was also able to prove the predictions of quantum theory and prove that Einstein was wrong. However, many critics argued that the experiment designed by John F. Clauser was not perfect experiment. There were certain problems were there were certain assumptions and biases were there that might have been able to help Clauser in reaching or arriving at a favorable conclusion. So in this regard, next contribution was made by Alain Aspect. Alain Aspect did nothing but simply basically improved the setup of Clauser, the experimental setup of Clauser to understand quantum entanglement, and he was able to remove all the loopholes, all the biases that the critics had found out in the Clauser's experiment. So in this regard, he made a perfect setup, and this experiment that was conducted by this improved setup of Alain Aspect was also able to basically prove that quantum entanglement is real, Einstein was wrong, and the Bell's inequality was proven wrong. Then, taking help of these principles, later on Anton Zeilinger, he made applications of the same principle in the area of teleportation, we have demonstrated for the first time that it is actually possible to teleport the quantum state of one particle to another location without transferring or moving the particle anywhere and without any kind of medium. So this is very, very important breakthrough that has been achieved by Anton Zeilinger, and this can serve as a basis for future quantum technologies, quantum machines that can be developed. So how these contribution of these three Nobel laureates are significant. So first of all, the major contribution is that now the debate that has been going on since almost past 100 years, that how to tackle or how to basically relate classical mechanics, Einsteinian mechanics with the quantum mechanics. So how now the debate has become one-sided, and the reason is simple, because the experiments have decisively demonstrated that entanglement is a real phenomena. It is not just a conceptual phenomena. It is not just a mathematical observation, but it is actually happening in real term. And second, this entanglement that has been proven experimentally work in accordance with the quantum theory. And third, as Einstein and the we can say Bill also has suggested that there must be some hidden forces acting as far as the quantum entanglement is concerned. They have now also been proven wrong, as there is no hidden forces as suggested by Einstein. So these are the three stellar contribution and significance of the experimental study of the scientists. Now, what is its applications and implications in India? So, as far as the quantum concepts, technology, and India is concerned, ISRO, DRDO, Department of Atomic Energy, Department of Science and Technology, all have been for a long time interested in supporting projects on quantum key distribution. And in this regard, scientific groups at the Raman Research Institutes as well as the PRL, that is Physical Research Laboratory in Ahmedabad, have made significant progress. And now, since the Nobel Prize has been awarded in this area, obviously there can be possibility of more funding that can be provided to work in the area of quantum computer and quantum physics, and that is why more and more significant we can say development can be expected in the near future in the world as well as in India, also in India as well. So what we can say basically in the conclusion, that the work of these three Nobel laureates today can help in developing quantum technologies of the future, for example quantum cryptography, quantum computation, and precise timekeeping, as is done in the case of atomic clocks. So that is all for this particular topic. I hope you understood all the basics of quantum physics, what was the rationale behind providing Nobel Prize to this year winners, and also what can be its possible implications in the future. So I hope you enjoyed the video. If you like it, please like, share, and subscribe. And also you can let us know in the comment box that what are the topics on which you want us to make videos, and we will happily make. Thank you very much.